And here's another example with a rate of change. So this time we've got the surface area of a cone, again in terms of its radius and its height, and R and H are both increasing, and we're trying to find the rate at which the surface area is increasing. So we're going to have to use try to find the rate of change, which is the surface area. So we're going to say that that's equal to how the surface area is related to the radius times the rate at which the radius is changing, plus the relationship between the surface area and the height times the rate at which the height is changing. Okay, so we're going to have to differentiate this thing once with respect to R and once with respect to H. And just looking at that square roots are fun things to differentiate. So let's write that as, oops, that should be a plus, pi R, and we'll write this as R squared plus H squared to the power of a half. This makes it a little bit easier to differentiate, I'm sure. Okay, so what have we got here? Let's jump in and do some differentiation. So it equals derivative of this thing with regards to R, so that'll be 2 pi R plus a bit of product rule here. So the derivative of the first one times the second one plus the first one times the derivative of the second one. Yep, it all looks pretty good. Times the derivative of the inside bit. Okay, because we want to differentiate the second bit, R squared plus H squared to the power of a half. Half comes down the front, drop the power by 1, times the derivative of the inside bit. Chain rule. Okay, and that's all got to be multiplied by how fast R is changing, which is 0.25. And then we add on, bracket, how S is changing with regards to H. Well, the first bit doesn't matter because that's a constant, and this pi R is also a constant, so really the only thing we're differentiating now is this piece here. So we're going to get a half pi R, R squared plus H squared to the minus 1/2 times 2H, and all that multiplied by 0.25. I managed to stay on the page, which is a bonus. So now really it's just a matter of substituting in the values for R and H and using the calculator to see if we can cancel anything out. So that half and that 2 can go out, that half and that 2 can go out, the 0.25 we might as well take out the front. If we've got a pi everywhere, pi, yep, so it's 0.25 pi out the front, and what are we left with? 2R is 6, because R is 3, plus 3 squared and 4 squared, that's just a 3, 4, 5 triangle, so that's going to be 5, plus this will be, and the negative is the same as 1 over, so that's 1 over 5, oops, times 2 lots of R is 9, what else we got, plus R times H is 12, again over 5, because it's that thing there will be 5, so that gives us what do we got, whole bunches of stuff with a pi over 5, a quarter, let's make that all over 20s in that case, so we've got 9 and 12 is 21, and a whole bunch of them, 76, yeah, I mean feel free to use a calculator to work all that out. Push the numbers in, kind of 11.94, and it's the surface area, so it's centimeters squared per second. Okay, and yeah, so that's how you do it. So I mean, this in here is just a bit of mucking around with the calculator really. So the key thing is that to figure out how the rate of change. So whenever you see the word rate, you've got to think it's time based. Okay, so the rate, find the rate. It tells you that it's time based. So this is the rate of change of S. It depends on the partial S, partial R, tied in with the rate of change of R, and then the same for the H's. And then it's just a matter of working through it from there.